Okay. Question number 1. Okay. The energy eigenvalues of a particle of mass m confined to a rigid one-dimensional box of weight L are n equal to 1 to 3, etc. Okay. If the walls of the box are moved very slowly towards each other, the rate of change of time-dependent energy dE2 by dt of first excited state is okay. So here given the question. Okay, so in the question, the energy eigenvalues of a particle. Okay, the energy eigenvalues of a particle of mass m confined to a rigid one-dimensional box of width L. Okay, and energy is En. Okay, if the walls of the box are moved very slowly towards each other, okay, then we need to find the rate of change. Okay, so we need to find the rate of change of time dependent energy dE2 by dt of first excited. Okay, so we need to find dE2 by dt. Okay, so we need to find dE2 by dt. So okay, solution. Okay, so let us consider a one-dimensional box. Okay, one-dimensional box of length L. Okay, of length L. Okay, now we know that when a particle is confined in a one-dimensional box, okay, in a one-dimensional box of length L, then the energy can be expressed. The energy is En is equal to n square pi square square by 2 ml square. Okay, this is the energy for a one-dimensional box. Okay, for a one-dimensional box where a particle is confined. Okay, in a one-dimensional box. Okay, now for n equal to 2, okay, E2 is equal to 2 square, n is equal to 2. Okay, n is equal to 2 square pi square square by 2 ml square, since the length is L. Okay, length is L. So dE2 by dt is equal to 4 pi square by 2 m. Okay, d by dt, we need to differentiate L inverse 2. Okay, we need to differentiate L inverse 2. Okay, so we get 4 pi square. Okay, 4 pi square 2 m minus 2. Okay, so in differentiate, okay, L inverse 2, then we get minus 2 L to the power minus 3 dL by dt. Okay, 4 pi square by 2 ml square minus 2 1 by L dL by dt. Okay, when simplify, L cube is L square and L, it's L cube. Okay, so dE2 by dt is equal to, we get minus 2 E2 by L dL by dt. Okay, here E2 is this. Okay, 2 square 4 pi square by 2 ml square is E2. Okay, so this term, okay, this term you can write E2. Okay, so this is the required solution. Okay, so next question. Okay, suppose in the question given that a quantum particle, okay, of mass m in one dimension confined to a rigid box as shown in the figure. Okay, here is a figure. Okay, given that a one-dimensional box of length twice L. Okay, a particle is confined in this box. Okay, so a rigid box as shown in the figure. Okay, using its ground state, and infinitesimally thin wall is very slowly raised to infinitely at the center of the box. Okay, so so in this box, okay, very slowly a thin wall is infinitely raised up. Okay, in this box at the center. Okay, at the center of the box, in such a way that the system remains in its ground state at all times. Okay, assuming that no energy is lost in raising the wall. Okay, the work done of the system when the wall is fully raised, eventually separating the original box into two compartments is, okay, so Okay, so we need to find, okay, so we need to find the work done. Okay, we need to find the work done of the system when the wall is fully raised. Okay, so initially the wall is length is twice L, okay, and the particle is confined in this box. Now after that we raise the wall, okay, infinitely, very smallly, okay, where the particle is confined and the box is remain until in its ground state. Okay, so we need to find the work done on the system here. Okay, so so we need to find the work done on the system when the wall is fully raised, okay, eventually separating the original box into two compartments. Okay, so we need to find the work done. So solution, okay, let's see the solution. Okay, so here we know that when a particle is confined in a one-dimensional box, okay, and the energy is n square pi square square by 2 ml square. Okay, this is the energy. Okay, when the particle is confined in a one-dimensional box. Okay, so here length is En is equal to n square pi square square 2 m. Here length is twice L. Okay, so 2L whole square. Okay, n square pi square 8 ml square. This is the now here the ground state energy. Okay, so here the ground state energy is E1 is equal to pi square square 8 ml square. Okay, this is the ground state energy in this box. Now again from the figure, okay, this figure, this figure, the final energy in the ground state when a wall is raised at the center, okay, and there are two compartments separated in two compartments. Okay, so the energy is, so here the length is L. Okay, so here length L. Okay, so En dash equal to n square pi square square by 2 ml square. Okay, so in ground state n is equal to 1, so E1 prime is equal to pi square by 2 ml square. Okay, this is the ground state energy from the figure 2. Okay, so therefore work done, so we know the work done is final energy minus initial energy. Okay, so final energy minus initial energy. Okay, so the final energy is pi square by 2 ml square. Okay, and the initial energy is pi square by 8 ml square. Okay, so we get 3 pi square square by 8 ml square. Okay, so this is the required work done. Okay, when a wall is raised at a one-dimensional box. Okay, next question. The ground state energy of 5 identical spin half particles which are subject to a one-dimensional simple harmonic oscillator, potential of frequency omega is. Okay, so in this question the ground state energy of the 5 identical spin half particles which are subject to a one-dimensional simple harmonic oscillator, potential of frequency omega. Okay, so at 5 particles, okay, 5 identical particles which are confined in a simple harmonic one-dimensional oscillator. Okay, so we need to find the ground state energy. Okay, so we need to find the ground state energy. Okay, so the solution is, okay, the solution, so we know that the energy of a harmonic oscillator, okay, energy of a harmonic oscillator is E is equal to m plus half of square omega. Okay, this is the energy of a harmonic oscillator. Okay, so now n is equal to 0, there are 2 particles. Okay, and n is equal to 1, 2 particles, n is equal to 1 particles. Okay, so therefore total energy in the ground state, okay, so total energy E is equal to, here energy is square omega. Okay, and In this, the energy is 3 square omega, and okay, 3 square omega, and here, sorry, yeah, here half square omega. Okay, so and here 3 by 2, n is equal to 3 by 2, so total is 2 particles, so n is equal to 0, half square omega. Okay, so 2 particle, 2 cancel. Okay, 2 cancel. Okay, square omega, and n is equal to 1. Okay, there are 2 particles, so 2 into 1 plus half of square omega is equal to a square omega. 2 into half square omega is equal to 5 by 2 square omega. Okay, so we get 13 by 2 square omega. Okay, so this is the required answer. Okay, 13 by 2 square omega.